All right, today we're going to finish section 1.1. We started talking last time about a preview of calculus and taking a look at the basic ideas of why calculus allows us to do more than pre-calculus. And the general sense that I hope that you took away from that is that we can simply do more types of things with less defined or rigid types of shapes. And so our shapes can be more variable, more fluid, more curved, those kinds of things, and we can actually work with them, but do a lot of the same things that we do with pre-calculus, just in different ways. So what we're going to take a look at first today is we're going to take a look at two different types of problems that can be done using calculus. And we're going to look at them from a pre-calculus perspective of approximation. So this isn't calculus, but this is where calculus is leading us to and why we want to be able to do it. So the first type of problem we're going to look at is called a tangent line problem. The tangent line problem talks about secant lines versus tangent lines, and we mentioned these in one of our examples last time. So a secant line is a line that cuts through a shape, right, like that. So in particular, what happens is you take 2 points on the shape and you connect them with a line segment or a line through them. Okay, that's a secant line. And you can do it for this graph just the same as you can do it for this graph, right? It doesn't matter what the shape is, it's still called a secant line. A tangent line, however, takes 1 point on the graph, like that, and it creates a line through that 1 point, just bouncing off of the shape. Now, over here on this graph, if it's bouncing off of the shape in 1 point, it might actually cross through the shape in another point. But the point of tangency is what you're usually given to start with. So for example, let me cut this and make the line a little bit narrower. So if you're given the point, for example, right here, and you were to draw the line looks something like that. And it doesn't cut through the shape again. But if you were given the point, say, right here, and you were to draw the tangent line, this tangent line would look more like this, and it would eventually cross through the shape again. So it isn't so much about it never crossing back through the shape. It's more about the fact that nearby this point, the slope of the line that you're drawing and the slope of the curve seem to be approximately the same. If you were to zoom in on your calculator and look really close to them, the line and the curve would look almost identical. Okay, so that's what we're looking at when we're looking at a tangent line. So taking a look at this idea, go ahead and split your screen, my screen, your paper, into two pieces. On the left side, we're going to talk a little bit about this. So in pre-calculus, we can find the slope of a secant line. We can use 2 points on the curve and calculate the slope between them. And in general, for that shape that I had drawn before, that's not great, but it's okay. It looks something like this. And we can take 2 points on the shape. I'll use red, say this one and this one. And we can draw a line between them. And you can calculate slope, right? Slope is calculated by using 2 points, finding their x values or y values, and you have the slope formula. If you remember, one version anyway of the slope formula is y2 minus y1 over x2 minus x1. Sorry, I had turned it on while I was driving because otherwise I wouldn't hear it. Okay, and on our graph, we can identify what those would be. So right here would be our x1, for example, and then this corresponds to a y1 right here. This would be our x2, and slightly higher than that over here was our y2. So those are the x2 and the y2s from our graph. Okay, sorry, it's a little bit tight. I should have moved it over a little bit more. So in calculus, however, what we've talked about is we can find the slope of a tangent line. And the natural sort of problem that comes about as you're thinking about it should be, okay, but when I had a secant line, I had 2 points and I had two x's and two y's, I had 2 points, right? But when you have a tangent line, generally speaking, you only have 1 point. So I can't do a change in y, I can't do a change in x because I only have 1 point, right? That's the problem that comes into play. So the way we do this, we do this by using secant lines. Where the points get closer to one another. So just to draw an arbitrary picture, we'll draw that same one. I'm not going to draw the grid around it, right, the axes. But if you imagine taking, we'll go with this point right here, this point as the tangent line we were looking for. Okay, and we're trying to find this line, right? The goal is to find this line, approximately speaking. So what we do is we take a point that's nearby, and I'm starting with a point that's further away just because it'll be easier for me to draw. So if I start with a point over here, my purple point, and I draw a line through there. Come on. Okay, give me just a second because I'll have to move it for it to make sense. That's not too bad. There we go. So there's a line. And we let the point that's the purple point get closer to the red one. So instead I do it this point right here, so it's blue now, right? And I'll draw a blue line. So my line looks like this now. And then I draw a point a little bit closer. So let's draw a green one. Do a green point. The green point's right here. And my green line will look like this. And you can imagine that as those colored points are getting closer and closer to the red, and they're getting, they're nearing it, that's getting really close to that secant line, or that tangent line, using secant lines that I was wanting. So that's how we go about approximating this tangent line's slope using pre-calculus. The other problem that we're going to look at is called the area problem. And the area problem we will not get to in this class until the last month of class, okay? So we will revisit this topic, but it's going to be a while. So again, split your paper. So in pre-calc, we can find the area of certain shapes. So tell me some shapes you know how to find the area of using just basic stuff from high school and middle school and maybe even some of the elementary stuff. What do you know to find of shapes? Squares, triangles, circles, right? Okay, so I'll write those down. Those are all good ones. Yeah, so things like squares, triangles, circles. And the one that we're going to focus our attention on is a variation of one you mentioned. We're going to look at rectangles today. in this example. And of course, there's lots of other shapes, right? We could throw in here parallelograms and trapezoids, and I mean, you could throw in all sorts of stuff, right? But there's certain shapes that you know formulas for, and if you don't remember them, you just go find them very easily, right? They have specific defined formulas. They're simple to use, very direct. Most of these are formulas, so let me mention that. So we use formulas. And most formulas, by the way, if you aren't aware, are based on the formula for the area of a rectangle. So most of which are based on the area of a rectangle. And what is the area of the rectangle's formula? Base times height, or you can remember it as length times width. Those are two different versions that show up at different points. The circle's a variation to this, obviously, right? It's not exactly based on the area of the rectangle in a most direct way. But the other ones you mentioned were squares, triangles. They're all based on the area of a rectangle. The same thing happens if you were to look at trapezoids or parallelograms, area of a rectangle. They all go back to that formula. So in calculus, then, we can use the area of a rectangle we'll say rectangle, so the area of rectangles to approximate the area under a curve. Then we let the width of the rectangle approach 0. And I'll draw you a picture. So I do need an XY axis for this to make sense. So let me put that in there. And we'll draw that same arbitrary curve. There's nothing special about this, but I use it a lot. We start at one end point, and we're trying to go to the other end point. You can call them whatever you'd like. And the idea that we want is we want to find, let's see if I could draw it straight. Move this one over a little bit so I can be there better. Something like this. We want to find the area of this region. You might be looking at that and saying, well, that's definitely not a rectangle. And you would be right. It's definitely not a rectangle. But if you subdivided it, right, like cut it in half, that's not perfectly in half, but it's okay. And then you cut it in half again. And then you cut these in half again. Do they start to look a little bit more like rectangles the more narrow they get? They do. And if you let the width of these rectangles be 0, right, or go to 0, right, get infinitely narrow, or you could say if you let the number of rectangles become infinitely many, right, infinitely many rectangles here, then we would actually have an approximation for the area under this curve by finding rectangles. And we would do each of them length times width, or base times height, every single one of them, and add them all together. And that would be an approximation for the area under the curve. And that's exactly what we will be doing when we get to chapter 4. And then we will be applying the calculus technique to doing that to make it smoother and easier and more accurate. Okay? It's probably worth mentioning that everything that your calculator can do, and a couple of you talked to me about having TI-89s with you as well. Even your TI-89s, everything that your calculator would do and actually give you these values is using numerical approximation. It's not using calculus. Your calculator does not know calculus. Okay? It knows numerical approximations for things. So as we encounter a couple of different places along the way where I say, hey, grab your calculator, I'm going to show you how cool your calculator can approximate this or whatever, it's doing stuff like this, right? It's using pre-calculus. It's using formulas. And it's using this limiting process of making things infinitely narrow or getting points infinitely close together. Okay, so we do actually have a couple of examples of things to take a look at where we are computing something. In particular in this section, the homework for this section inside of WebAssign, which I have not heard anything still yet from WebAssign. So at this point, if you haven't already created a code, go ahead and just create your code. Go out there, Google WebAssign, create your access, and just get started. Hopefully it will integrate into Canvas, and we'll be able to do that in the future. But for right now, it's no different than any of my other classes have had to do, and it'll be just fine, okay? So go out to WebAssign. You will have this section 1.1 that will be due on Wednesday, okay? So make sure that you're going out and you're taking a look at this. Most of the questions have you do one of two things. They ask questions like this, I should say. They ask you to decide, is this problem a pre-calculus problem, or is this problem a calculus problem? If the calculus problem is a pre-calculus problem, they ask you to actually find the exact value, because you'll be able to do it because you've had pre-calculus, okay? Maybe not a course titled that exactly, but you've had concepts that were previous to calculus, okay? It's the same thing. If it's a calculus concept, they'll be asking you to do some approximations for things. So this one right here, I've asked the question slightly differently. So my question says, decide if the problem can be using pre-calculus or calculus. If it's pre-calculus, we're going to solve it, and we're going to explain why. And then the explain why part, that's what I wanted to say. We're going to actually explain why it's going to be done that way. And then if it's actually calculus, we're going to use the numerical approximation, and we're going to actually also, in some sense, sort of realize why. Why is it using one or the other? So here's our first one. We have an equation. It says, consider the equation f of x equals 4x plus 3. What is the slope of this curve at x equal to 2? So first, pre-calculus or calculus? Pre-calc. Why is it pre-calc? Say again? We can get the exact value. How come? What about this means that we for sure can do that? That's not why. We do have a value for x, but putting that value for x in is not necessarily what we're going to be doing in this problem. Yep?
It's a line, so it's a constant slope.
Yeah, it's because it's a line. If this equation had said 4x squared plus 3, we wouldn't have pre-calculus. It would be calculus. So the fact that this is a line is what tells us this. Okay, so this is pre-calculus. And it's because it's a line. It's a really important thing to keep in mind. Lines are pre-calculus. Any other kind of shape that we work with, they're not, for the most part. So looking at this one, it's really tempting to see x equal to 2 and plug it in. And I agree with you, because it says x equal to 2, I've got an equation, and that's what we usually do when we're given an equation and we've given a value. That's not what the question's asking for. This question is asking us to find what? The slope. What's the slope of this line? 4. Does it matter that x is equal to 2? It actually doesn't end up mattering in this problem, right? Any x value that they would give us, we would have the same slope because it's a line. Yeah? So be careful not to do more work than what the problem really wants you to do, because it's really tempting. But this one is the slope. It's identifiable. The slope is 4. And it doesn't matter that it's at x equal to 2. Now, if it were a curve, it would matter, right? So imagine my curves that I had over here. Oh, I wanted the ones I first did today. Here, that was it. Right? If I draw this tangent line where I've drawn it on the second picture, and if I drew the tangent line at the dot down here, would they have different slopes? They would, right? So if I've got a curve, it really matters that they give me that x value. If I have a line, it doesn't matter in the slightest. So just be careful that you're not being led astray by the information presented. All right, so this one's a little different, though. In fact, this one I've already got some tables set up for us. Because if you take a look at this one, it says consider the equation. F of x equals 3x squared plus 2x minus 4. And it says, what is the slope of this curve at x equal to 2? The question actually is the same question as we had before. It's just a different equation. And this equation is what? It's calculus. We're going to use calculus. What is this an equation of? Do you remember? It's a parabola. And in particular, even if you didn't know it was a parabola, hopefully at least you're looking at it and saying, well, it's not a line, right? That's the important part. It really doesn't matter so much that it's a parabola, but it's not a line. So this is going to use calculus. And it's because it's not a line. And you can more specifically say it's a parabola or something like that. But it's not a line. So we're going to have to do this problem differently. In particular, you saw what we had described before about how we want to let the points get really close together and find the slope of those ever increasingly nearby one another points. That's what we're going to do. So we have the point at x equal to 2. And there's a really nice way of doing this. We want the points to get really close to 2 in a very sort of standardized way, because then we don't have to think every single time, what about this one? What am I going to do with this one? Well, they're always going to be the same. You can do the same process for all of them. So here's what you do. One of these tables I have set up is going to get close to 2 and be slightly bigger. So it's going to have like 2.1. That's pretty close to 2, right? It's definitely bigger than 2. But I could be bigger than 2 and get closer to 2 than that by doing 2.01. And I could get even closer if I do 2.001. Those are x values getting very, very close to the number 2 from the right-hand side, or the slightly bigger side of 2 on the graph, right? But I do need to be careful that I approach from both directions of the graph. I've talked about coming from the right-hand side of the graph, the slightly bigger side of 2, and I need to come from the slightly smaller side of 2. So on my other table over here, I can do values like 1.9, 1.99, and what do you think the third one's going to be? Yeah, 1.999. Okay, now in my hurry to get here today and grab the things from my office and try to get here as soon as I could, I didn't grab my calculator, but that's okay. So we're just going to talk through how we go about doing it. It's not something you even need a graphing calculator for. So if you have a scientific one or a graphing one, go ahead and get it out so you can run through the process. In order to find the slope of a line with pre-calculus, we need x values and we need y values. How can I find the y value if the x value is, we'll do the first one, 2.1? Yeah, that's the one you were wanting to do before, isn't it? Yeah, we're going to just plug it in. And not only that, we could actually even start with x equal to 2 because we don't have that one either. X equal to 2 up here at the top. So take this equation, and if you're using a graphing calculator, you can actually put the 3x squared plus 2x minus 4 and y1 in your calculator. If not, you can just put the number 2 in as you go, right? You can do 3, then you can put parenthesis 2 squared plus 2, parenthesis 2, and then minus the 4, right, like that. We want to plug in the number 2. We'll start with that one. So if I plug in the number 2 into this equation, right, 3 times 2 squared plus 2 times 2 minus 4, what do we get? So f of 2, rather here, is 12. Does everybody have that? That work okay? Okay, let me show you a cool calculator trick while you're here. For those of you who do have your TIEs for me, there is a way that you can use this equation and you can put 2 into the calculator without having to type it all in every single time. It's called the table. And your table is often already set up for you to automatically give you some x values and y values, and we don't necessarily want those x values and y values. We'd like to be able to pick, right? We'd like to be able to do 2.1 and 1.9 and those kinds of things. So the way that you can do that is you can go underneath table set. So it's second window. So if you hit second window, you've got a screen that says table setup. Does everybody see that who has those kind of calculators with them today? Okay. The first, it says auto ask. So it says independent auto ask, dependent auto ask. You see that? The first one should say ask. The second one should say auto. I don't think it can do anything with your TI-89. I'm sorry. It's okay. You're going to find another option for us, right?
Hopefully.
I hope so too. Okay, so the first one should say auto, and the second one, the first one should say ask, the second one should say auto. So if you go to it, you can just arrow to the right and press enter onto the ask. That one's good. A TI-82, okay, you can just type them in though, that's fine. And you can type yours in on yours too. it'd be okay. Yeah. TI 82, 83, 84, any of those. And if you haven't purchased one and you want to purchase one, if you have several classes to take, you can usually get them for about 30 to 40 bucks on eBay. Yep. Yep, you got yours. Colton, yours is already set up, right? Yours is good. Oh, Cassie, I don't know.
Okay.
So you'll have to look. Okay. If you do have this set up, you can actually put into your table, so you can hit second. At this point, you can hit second graph, and you'll have a table that's blank. And you can just type in 2.1, 2.01, 2.001, 1.9, 1.99, 1.999, and it'll spit out to you 6 answers, just like that. If you don't have it set up like that, or if you're using a calculator that I'm not working with you today on or whatever, you're just going to plug it in, right? So you're going to plug in one of them at a time, and you're going to plug in 3 times 2.1 squared plus 2 times 2.1 minus 4. And then you're going to do the same thing with 2.01, 2.001, and then all the 1.9s. Okay, so as you do that, and for those of you who don't have your stuff with you today, I'm going to let you know what I have. This is 13.43, 12.1403. So we're going to go to 6 decimals of accuracy. If we have to round, we round to 6. Okay, so far these don't have to round because they stopped at 2, they stopped at 4. The next one actually I think stops at 6, but even if it didn't, we would stop writing them down at 6. So this is 12.014003. And if you're in that screen and you're like, but my screen only shows 4, just use your arrow to arrow on top of the number, and it will show you a further, like a longer value at the bottom of your screen. Okay? The 1.9s are 10.63, 11.8603, and 11.98603. Okay, now we have an XY ordered pair that we really care about. That's the one at the top, right? This one right here is the one we care about. X equals 2, Y equals 12. That's the one we care about. And we have these others that we made up. Agreed? I mean, they're made up. There's really nothing special about 12.1. If you had used 12.3, it wouldn't be wrong. It'd just be a different approximation. Agreed? Okay, so these are ones we made up at the bottom. We're going to use the one we care about at the top, and we're going to use these one at a time to find slope. Okay, so slope, as we mentioned earlier, is y2 minus y1 over x2 minus x1. And I'm going to call the 12 and the 2 the x1 and the y1. Again, could you call them x2 and y2? Sure, it doesn't matter. Just pick one, stick it in there. I'm going to use x1 and y1. So we're going to use them one at a time. I'll show you what it looks like for the first one. And we're going to do, so my first slope, I'll call it M1, is 13.43 minus 12, those are the two y values, over 2.1 minus 2. This is the slope if I use the point that I was given and the point that I made up, the first point I made up. Okay? That's what it would look like. Your second one would be 12.1403 minus 12 over 2.01 minus 2. And our third one in this list is 12.014003 minus 12 over 2.001 minus 2. Does everybody see what we're doing, where all those values are coming from? And your calculator can do all that, right? Be a little bit careful, right? Depending on the version of the calculator and so forth, you might need to put parentheses around the top or parentheses around the bottom to make sure that your calculator doesn't inadvertently divide when it should have subtracted something first, those kinds of things. So make sure your calculator is being a little bit careful. all the numbers you're getting should be close together, right? If those slopes are very far apart, there's probably a parenthesis problem, is probably what it is. Or you might have typoed by a decimal or something like that too, left a decimal out or put the decimal in the wrong place. So if we take a look at these three values are actually 14.3, 14.03, and 14.003. And what is happening as you head down this table? What does it look like the slope is approaching? Looks like it's approaching 14, right? I mean, we're getting pretty close to it, it seems like. If we were approximating, we would probably at this point say, hey, look, 14.03 is pretty much 14, right? We would probably do that. So it looks like it's 14. Now we're going to do the same thing with the 1.9s. I'm not going to write them all out, but they would work the same way, right? Where I have this 13.43, it would say 10.63. And where I have this 2.1, it would say 1.9. And we can do that the same way with all three of the values over here in this table. Yeah? And if we do that, we'll get values that look like this. 13.7, 13.97, and 13.997. If you go down this table, what does it look like it's getting close to? Yeah, it looks like it's getting close to 14 again. Now, does it have to be the same thing for both tables? It doesn't have to. But most of the ones we work with, especially ones that are like parabolas, polynomial kind of functions, they're going to be. Like that's the nature of those kinds of functions. So the answer to our question, what we expect then, is that the slope is approximately 14. And for those of you who maybe have had some calculus exposure in the past, you probably know some shortcut methods in your mind, too. I'm not going to talk about them now because we're not there yet. To be able to look at this equation and say, oh, yeah, that makes sense from what I know from seeing some ideas before. Any questions on this one? Okay, so this assignment's finished, which means that it's now assigned in WebAssign. Okay, it's been already open in WebAssign, but it will be due on Wednesday.